Welcome back to eCoreAcademy, everyone. My name is Anita Raj, and I am one of the teachers and co-founders here, along with my younger brother, AJ Raj. As you can see, we're bringing to you all a new Algebra 2 lesson today, and it is called Rational Functions and Their Graphs. This is going to be an introduction video to this concept. The special characteristic of this video is that we're actually skipping forward a whole unit. We're not done the polynomials unit yet, but we're getting into the rational functions unit. You might be wondering, why are we doing this? Well, I'm obviously going to go back and record the videos from the last unit later, but we got some special requests from some students in India who are preparing for their final exams, and they requested this lesson specifically to help them out. So I'm here to do what I can to help prepare you, and this little series that I'm going to have, which is going to consist of, I think, about 5 videos on this topic, will hopefully set you up for success on that part of your exam. So this first video is going to be an introduction to this concept. The next one is probably going to be focusing on discontinuities. The one that follows that will be on graphing. The fourth one will probably be on asymptotes. And the fifth one, I'm still debating about that, but we'll see how the response is to these 4 videos, and we'll probably do one on problems, just practice problems, including regular mathematical problems and then your real-world applications. So in this first video, again, we're going to be introducing this concept, and we're going to be learning about basic characteristics of different rational functions. We'll be understanding what is a rational function. We'll be looking at some graphs, 3 to be exact, and we'll be trying to understand how this concept is different from the typical polynomials we looked at last unit. By learning these basic skills about what a rational function equation looks like, along with what a graph looks like, will better help us determine where the discontinuities occur, where the asymptotes are, what the asymptotes are, and then when we understand topics like this and master them, we can obviously apply them to real-world applications, and we can do that through modeling using rational functions. So before I get into the video, there are 2 things I want to do. First, I just want you to look at the image I have up here. I like including these little jokes. There's a graph, and you see a graph of a function. The function itself is the solid white line that looks like a curve. As you can see, there are 2 parts to it, and then there's a dotted or a hashed line, a vertical line, and you see these 2 curves are approaching this line, but they're actually not touching it. They're going to continue to infinity, and they're never going to touch that line, but they're just going to get closer and closer to that hashed line, and they'll never touch each other. This line, this hashed line, is called an asymptote, and we'll learn about it later on, but if you see there's a wizard standing there, and he says, "You shall not pass." So it's almost saying that these graphs are never going to touch, these 2 parts of the function, these 2 curves are never going to touch the vertical asymptote, they're never going to pass it, and they're never going to touch each other. So I thought that was a joke. And before I get into the video, again, please do what we usually ask you to do. Please like the video, subscribe to the channel, hit the post notification button, drop a comment down below, and share using all of our socials. So let's get right into the lesson. These first 2 slides that I show you are going to be pretty heavy on notes and some terms that I want you to familiarize yourself with. So first, let's talk about what rational functions are. This is the whole concentration of these next few lessons. So obviously, we need to understand what is the purpose of these lessons, what are rational functions, what are we going to be working with. So a rational function, we can think of a function as y equals a function, or we can think of it as f of x. So in this case, I'm just denoting it as f of x. So a rational function, f of x, is a function that can be written as f of x is equal to p of x divided by q of x. See, I highlighted that because I want you to keep that in mind. So we have f of x. F of x itself is our rational function, and then we have 2 more functions, which are called p of x and then another one called q of x. And f of x is equal to this function p of x divided by q of x. So p of x is almost like our numerator, q of x is our denominator, because this is a fraction. So I'll just write it in terms like this, because it might be easier for you to see. F of x is equal to p of x over q of x. Same thing. All right. P of x and q of x are polynomial functions, and q of x does not equal 0. So let's break down what that means. So remember, p of x and q of x are polynomial functions. Remember, that's what we were going over last unit. Polynomial functions are just a series of terms, and remember, each term is going to include a constant, which is going to be your coefficient, which is the number that comes before your variable. It's usually a number. It could be an integer, a fraction, positive or negative, but it is just a number. It's a constant. It's not a variable. It doesn't change. And what comes after it is the variable. Usually we denote it as x, but you might see some other variables. For our purpose, we're just going to be working with a y-coordinate and x-coordinate, so the variable is going to be x. And then it also includes an exponent. So the variable is usually raised to an exponent. For our purposes, we've been working with positive integer exponents. You might see fractions, you might see fractional exponents, but for our purposes, for a polynomial, we define a polynomial function as having exponents that are whole numbers. For our purposes, positive whole numbers, or positive integers. And these each are a term. So a term consists of our coefficient, which is a constant, our variable, which is usually x, and then that variable raised to an exponent, which is usually a positive integer, and that makes up one term. Polynomials will usually have multiple terms. They might not always have multiple terms, but they usually do, and these terms are separated by addition or subtraction. And terms are usually arranged in descending order, so the term with the highest degree goes first, and then you just arrange them. That's just the proper way to write a polynomial. That's polynomial standard form. And we're being told that p of x and q of x are these polynomial functions. For example, we could say something like p of x is equal to x minus 4, and then q of x could be equal to something like x squared minus 13x plus 14. I'm just making these up. So those would be examples of polynomials that p of x and q of x are. And because p of x is the numerator and q of x is the denominator, our rational function is equal to x minus 4 over x squared minus 13x plus 14. So that's just an example. So these two are polynomial functions, and q of x cannot equal 0. So I want you to make sure that you keep this in mind. Our function q of x cannot equal 0. Functions can be equal to constants. For example, you could have a function f of x equals 1 or f of x equals negative 1/2. Those would just be horizontal lines, and those do pass the vertical line test, so they are functions. But in our case, q of x cannot be equal to 0, and if you think about it, like we were saying, f of x is equal to p of x over q of x, so that's a fraction. If q of x is equal to 0, we end up having a situation where the denominator is equal to 0. And if we remember these basic rules we learned, I remember learning them in like pre-algebra or algebra 2, if you have 0 divided by a number, so 0 is this O here, and the number is going to be n, this is okay. So this is, you can have this is equal to 0. However, if we have a number, which is n, divided by 0, think of it like no, so no, if you see what I'm saying here. So this is no. The numerator, if you want to think of it in terms of like letters, so no, no, this cannot happen, this is undefined. And if you put a number divided by 0 in your calculator, you're even going to get error. It's just undefined. It's undefined in our world of math. So q of x cannot equal 0, because if p of x is some polynomial and you divide it by q of x, which is equal to 0, you're going to get an undefined rational function, and that's not rational anymore. That's undefined. So that's why q of x cannot be equal to 0. So your rational functions can be expressed as a ratio between two numbers. So in our case, I've been calling it a fraction, but a ratio is pretty much the same thing. It can be expressed as a ratio between two numbers. Our two numbers are going to be p of x and q of x. They're polynomial functions, and with our rational function, we're pretty much representing the relationship between these two functions. A ratio, in other words, is how many times one number contains another. So my best example for this is apples and lemons, because I saw this somewhere on the internet. So let's say you have 2 apples, and for every 2 apples you have 6 lemons. Keep in mind that you can also, I wrote this with a colon in between, you can also write this as a fraction. 2 apples over 6 lemons. So let's say for every 6 lemons, you have 2 apples. That's pretty much what this ratio represents. We can simplify this ratio by dividing both sides by 2. So if we divide 2 by 2, we get 1. We divide 6 by 2, we get 3. So we can simplify this. Instead of saying for every 2 apples, we have 6 lemons, we can say for every 1 apple, we have 3 lemons, because we're just simplifying it. So we're pretty much representing a ratio here. So this can also be rewritten as 1 to 3. And in a similar way, and in this way, we're saying how many times can 2 go into 6? So how many times how many times does one number contain another? Well, 6 contains 2 3 times. We rewrote it as 1 to 3. Similarly, with p of x over q of x, we're pretty much trying to determine how many times do one of these functions, p of x or q of x, contain the other one, p of x or q of x. So it's going to depend on which one is the larger number and which one is the smaller number. If p of x is the larger number, we're trying to determine how many times does p of x contain q of x, and if q of x is the larger number, we're trying to determine how many times does q of x contain p of x. So that's the basics of rational functions. Let's get into what graphs are going to look like and what we should expect before we get into the next few slides, where we're going to be looking at graphs exclusively. So graphs of rational functions. Graphs of rational functions often have breaks in them because the denominator of f of x cannot equal 0. So graphs of rational functions, for the most part, we've been looking at lines from linear regressions or linear equations, y equals mx plus b. We've been looking at parabolas, which are quadratics, which is y equals x squared. We've been looking at cubics, y equals x cubed, which was it was like this. I don't know how to describe the graph, but we were looking at lines, which look like that. We've been looking at parabolas, which look like that. We've been looking at cubics, which look like that. And these all are continuous, meaning they don't break anywhere. If you look from left to right, if you look across the domain, we focus entirely on the domain. If you go from left to right, the domain has been negative infinity to positive infinity because every x value has a corresponding y value. So these graphs are continuous. We don't see any kinds of breaks in them. We don't see any kind of x value that does not have a corresponding y value. However, rational functions don't always adhere to these rules of being continuous, of having a y value for every single x value. They often have breaks in them, meaning the graph will continue boop, 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 boop for a bit, and then you'll have a break because that x value does not have a corresponding y value. So if you plug that x value back into your function, like the rational function equation, you don't get a y value. You'll get something like undefined, or you might have something cancel out, and I'll show you exactly what I mean. But those scenarios cause there to be breaks in the graph because there is no corresponding y value for that x value you put into the function. So if you actually plot that on a coordinate plane, if there's no y value, you can't plot a point there for your function. So there's going to be a break in the graph. It's going to be something that we call discontinuous. And this is usually because the denominator of f of x cannot equal 0. So if we had an example where we had a function such as f of x is equal to x minus 2 over x minus 3. This would be a rational function. X minus 2 is your p of x. It's a polynomial. And x minus 3 is your q of x. It's also a polynomial, and it's not equal to 0. However, if we set x minus 3 equal to 0, we find that if we add 3 to both sides, we get x equals 3. So on our coordinate plane, if we plug in the point 3 for this, we're going to end up plugging it in the numerator. 3 minus 2 is equal to 1. That's fine. If we plug it into the denominator, 3 minus 3 is equal to 0, but that's problematic because our denominator cannot equal 0. If it does, this function is undefined at that point. Because the denominator of f of x cannot equal 0, we're going to end up plugging 3 in for x, and we're going to end up getting undefined, which is not a specific y coordinate, meaning we don't have a point when x is equal to 3. We don't have a corresponding y coordinate. That's going to cause there to be a break in the graph of f of x. Breaks can be caused by asymptotes and holes due to values x cannot equal and due to common factors between the numerator and denominator. So again, breaks are places where the graph does not have a point. Breaks can be caused by asymptotes, which we were talking about when I showed you the introduction slide. So in the case that I just showed you with f of x equals x minus 2 divided by x minus 3, asymptotes are going to be vertical. Usually they're going to be vertical or horizontal lines. For our purposes, we're first looking at vertical lines. They're vertical lines that are at a x value. Remember, vertical lines are always x equals something. Vertical lines have an undefined slope. So you're always going to have an asymptote at something like, for this case, we would have an asymptote at x equals 3. So they're going to be vertical lines. You usually see them dashed or hashed on a graph. And if you saw in that first image I was showing you, the curves were approaching that line, but they never actually touched it, because the function doesn't have a value at x. It's undefined at, the function doesn't have a value at 3. It's undefined at x equals 3. Therefore, it doesn't ever touch that x equals 3 vertical asymptote, because it doesn't even have a point there. It just approaches it as you get closer and closer to 3 from the left or right side. So these vertical asymptotes are caused by values x cannot equal, because we cannot have x equal a value that causes the denominator to equal 0. Also, you're going to have holes. So holes are going to be like a normal, usually in Algebra 2, we work with holes in linear equations, but you might also see them in other rational functions. Not linear equations, but when you simplify the equation, it becomes linear. But what happens is you'll have a graph, and then it'll be continuous, it'll look normal, and then suddenly you have an empty hole in it. And you might be wondering, what does this mean? Well, it means that x doesn't have a value at that point, because what happens is when you have your rational function, oftentimes you have rational functions that look like this. So f of x is equal to x minus 2 times x minus 3 over x minus 2. We can actually simplify this because the x minus 2's are both factors, and they common factors, and they cancel out. So whenever you have an instance like this where there's a common factor between the numerator and denominator and you can cancel them out, you're going to end up having a hole at that point. So we'd end up having a hole at x minus 2 equals 0. And if we add 2 to both sides, we'll have a hole at x equals 2. So those are the two kinds of breaks we're going to be working with for now. We're going to be working with vertical asymptotes, which occur when you look at the denominator, and then holes, which occur when you have a common factor between the numerator and denominator. These breaks make the graph discontinuous, and it helps to find them before graphing the rational function. So what does this word discontinuous mean? Because these asymptotes and holes can make a graph discontinuous. Well, you'll get more into continuity in pre-calc when you start talking about calculus at the end of your course, because I actually just did that. So discontinuity is pretty much going to be, for our purposes in Algebra 2, it's going to be a break in the graph. It's what makes the graph kind of, a continuous graph has a y-coordinate for every x-coordinate. So every x-coordinate is defined, it has a corresponding y-coordinate. The domain is going to be negative infinity to positive infinity. However, discontinuous functions don't have the same properties applied to them. The domain is not going to be from negative infinity to positive infinity, because there are going to be x values where you don't have a corresponding y value. So that's going to break up your domain because there are breaks in the graph. So when a function is discontinuous, there are multiple factors that can cause this. It doesn't have a limit. You'll learn what a limit is when you get to pre-calc, but it doesn't have a limit. It doesn't have a actual defined value at that point. For our purposes in Algebra 2, we're going to be focusing on that. A function for us is discontinuous when it doesn't have a value at a given x coordinate. And then the third one is when the limit and that point and a limit and the value of the function at that x coordinate are not equal to each other, and you don't have to worry about that either. So for our purposes, a graph is discontinuous when the x coordinate does not have a corresponding y coordinate when we plug it back into the rational function. And it will help us if we look at the function that we've been given, we figure out where do these breaks occur if we do have these breaks before we even graph the rational function, because we are going to be required to be able to graph these rational functions, and we need to be able to represent vertical asymptotes and holes if they do occur in that graph. Lastly, graphs exist within the domain of the function. So zeros in the denominator create vertical asymptotes. So graphs exist within the domain of the function. Therefore, what this means is that we have to determine where there are going to be breaks in the graph, because we're not going to just have a random point that pertains to this function at a point where the function doesn't even have a value. That's what this is trying to say. So let's say the domain of a given function is negative infinity. Let's say a given function has a vertical asymptote when x equals 0. So the graph just doesn't have a value when x is equal to 0. It's undefined at that point. So what's going to happen is your domain is from negative infinity to 0, union 0 to infinity. So we're going to use interval notation. I'll be showing you how we do that on the next few slides. But graphs exist within the domain of the function. So the graph is always going to have a point within the domain that you specify of the function, which is when we use interval notation. It's not going to have any kind of points where the domain does not exist for the function. That's what we're trying to say. Where x does not have a value, x is undefined for the function. It's not going to have a point there. So zeros in the denominator create vertical asymptotes. So x cannot equal a certain value because if you plug it in, it creates a 0 in the denominator. The function becomes undefined. You don't have a y-coordinate, so you don't even have a point to plot there. So you end up getting a vertical asymptote. And remember, vertical asymptotes go straight up and down. Usually, the equation for a vertical asymptote is x equals some value, a constant value, x equals 3, x equals -5. It has an undefined slope, and it'll represent the vertical asymptote. And remember, asymptotes are a line that continually approaches a given curve but does not meet it, like we saw in that first picture. Those two curves are approaching the vertical asymptote. The vertical asymptote straight, again, up and down, undefined slope. It's a line that will just continue to infinity along that x value. So if it's x is equal to 5, it's just going to be straight up and down for all values of x equals 5 through the positive y coordinates and through the negative y coordinates. So the curves will continuously approach it, but the curves will never actually touch it because the function doesn't have the function's undefined at that x value. And then a hole is just an empty circle in a graph that's caused by a common denominator between the numerator and the common factor between the numerator and denominator. Okay, we're going to look at some examples now. This is the first of 3. So this is going to be a rational function graph. So first we're going to look at the following graphs, find the value when the denominator equals 0, and then we're going to state the domain. And we're going to do the same thing for the next 2 problems as well. So we've been given the equation of this rational function. It is y equals x squared divided by the expression x squared plus 1. And as you can see on the screen, I kind of blew up the image, but that is how this function looks like when it is graphed on a coordinate plane. So when is the denominator equal to 0? So we have to find the value when the denominator equals 0. Well, in this case, our denominator is x squared plus 1. So x squared plus 1, we would set that equal to 0 to find out when the denominator is equal to 0. We're going to subtract 1 from both sides. So we get x squared equals -1. And then to get x by itself, we're going to do the opposite of squaring it. We're going to square root it. So we're going to square root x squared and get x. And we're going to square root -1. And you might be wondering, we can't do that because -1 is a negative number. You can't take the square roots of the negative numbers. And you're perfectly correct. In this case, the square root of -1, as we know, is the imaginary number I. So if we square root -1, we get positive or negative I, because remember, when you square root a number, you can take the principal root of it. You can also take the negative root of it. So we get plus or minus I because I times I is equal to -1, and negative I times negative I is equal to -1 as well. But I want you to keep in mind that when we set the denominator equal to 0, we're trying to figure out where the vertical asymptote is going to happen. And the vertical asymptote is a vertical line that's hashed, and you're going to see a curve approach it, but you're never going to see the curve touch it. Well, do we see any kind of vertical asymptote here? Because the vertical asymptotes make the function discontinuous, meaning there's going to be a break in the graph. So one part of the function might be approaching one value, and then you might see another part approaching a different value, but they're not going to even touch each other. But in this case, our function's continuous because it just keeps going. All points are connected. All parts of the function are touching each other. There's a bit of a dip, but all these points are still touching each other. It's continuous. So why is it continuous? Why don't we see any vertical asymptote? Well, because the solution where we got x equals positive or -1, it's not a real number because I is an imaginary number. I is not a real number. But we're graphing on the real coordinate plane. We don't have one axis representing i's imaginary numbers. It's just all real numbers on this real number plane. So there is no asymptote because we're graphing on the real number plane. So just keep that in mind. And then our domain, because there is no asymptote, because there is no break, no disruption at all. Think of it like that. There's no disruption in this graph. It's continuous, not breaking. All the points are connected to each other. So the domain is going to continue from negative infinity all the way to positive infinity. Okay, so let's look at this next one. As you can see with the function that we've been given, it looks like a line. It looks like a linear regression. But what is different about it is that you see there's a hole at x equals -2. So when x is equal to -2, I know the graph doesn't show it because when I actually graphed it online, the application didn't actually show the hole. So I drew a circle. So there's actually supposed to be an empty circle there. So make sure that when you graph it, and when I'll actually be doing graphing problems with you in a later video, we're going to actually make sure we emphasize that there's a hole there in the function. So we're going to do the same thing. We're going to look at the following graphs, find the value when the denominator equals 0, and then we're going to state the domain. So the equation of this function is y equals x plus 3 times x plus 2 divided by x plus 2. So these are all expressions put in separate parentheses. So first we're going to determine when the denominator is equal to 0. So in this case, the denominator is the expression x plus 2. So we're going to set that equal to 0. X plus 2 equals 0. Simply, if we subtract 2 from both sides, we get x equals negative 2. However, you might be wondering, okay, isn't there supposed to be a vertical asymptote at x equals negative 2 because that's the denominator? Well, if you look at the rational function, it's x plus 3 times the expression x plus 2 divided by x plus 2. Well, you can see that the x plus 2's are common, or shared factor, so a common factor in both the numerator and denominator. So if we were simplifying this, what would happen is these x plus 2's are common factors, so they would cancel out. We could rewrite this rational function as y equals x plus 3. And as you can see, this is similar to y equals mx plus b, which is slope-intercept form, which is what gives you your line. So that's why you see a line when we graph it. However, this is an ordinary line because we have that x plus 2 common factor that we got rid of, and we can't just ignore that. So what's going to happen is the domain is actually going to be equal to negative infinity to negative 2. Then there's going to be a break because this function is going to have it's not going to have a value. It's going to be undefined at negative 2. There's going to be a union, but then the graph is going to continue from negative 2 to infinity. So it's going to be perfectly fine and just continue. So notice how the numerator and denominator of this function have a common factor of x plus 2, which we talked about. They cancel out with each other, leaving the rational function simplified as y equals x plus 3. So this is going to cause that factor to cancel out like we were just saying, and there's going to be a hole at x equals negative 2 in the graph. Because x plus 2, like we said, we set that equal to 0 because it was the denominator. We subtracted 2 from both sides, we got x equals negative 2. If there was no common factor, x equals negative 2 would be your vertical asymptote. But because there is a common factor and x plus 2 is the common factor, there's instead going to be a hole at x equals negative 2. Okay, and let's look at our last graph. This one is similar to the one we saw at the very beginning. There are two curves, and they're approaching x equals 2. So there's going to be a vertical asymptote at x equals 2. As you can see, what I did was I drew a line, a vertical line, which represents our vertical asymptote, but I didn't just do that. I also hashed it because you're representing that this isn't an additional function that's being graphed on the same set of axes. This is instead of vertical asymptote. So make sure you hash it, and I'll be showing you that in a future lesson on graphing. So in this, we're going to look at the following graph. We're going to find the value when the denominator equals 0 and then state the domain. So the equation of this rational function is x plus 4 divided by x minus 2. So this rational function is going to be y equals the expression x plus 4 divided by the expression x minus 2. So let's first find when is the denominator equal to 0. So in this case, if we look at it, x plus 4 and x minus 2 are two simplified expressions. We can't factor them further, and there is no common factor between the numerator or the denominator. So we're just going to take the denominator, which is x minus 2, and set that equal to 0, then add 2 to both sides, and find that x is equal to 2, and when x is equal to 2, our denominator is 0 or undefined. That is why the vertical asymptote is at x equals 2. So when you don't have a common factor, you're going to just take the denominator, set it equal to 0, and you'll figure out where the vertical asymptote is. So in this case, the vertical asymptote is when x equals 2, which is when we plug 2 into our rational function, we end up getting 2 plus 4 divided by 2 minus 2, which is equal to 2 plus 4 is 6, 2 minus 2 is 0. So we end up getting 6 divided by 0, which is undefined. So this rational function just approaches 2 from the right and left, but it never is going to be equal. X is never going to be equal to 2. So our domain is therefore going to be negative infinity all the way to 2, because 2 is where that vertical asymptote is. That's where our function breaks, goes in opposite directions, does not touch, doesn't even have a point there. And then it's going to continue from 2 to positive infinity. Notice how, like the last problem, there's a parenthesis at 2 because 2 is not included in the interval. If there was a bracket, then it would be included. Because there's a parenthesis, 2 is not included. X equals 2 is not included. You also use parentheses with positive and negative infinity. So just keep that in mind. Alright, that's all I have for you today. I hope you enjoyed the video. If you did, please like, subscribe, and hit the post notification bell. Drop a comment down below and share using our socials. Please also check out our website and Gmail. Thank you for joining me and stay tuned for the next few lessons.